When we think of a cliff, we tend to picture something solid, permanent, unchanging, right? But that's not really the whole story. In fact, cliffs are some of the most dynamic, ever-changing landscapes on our planet. They're locked in this constant, slow-motion battle with nature itself. So let's dive in and see what that battle actually looks like.
So what does it actually take to bring down a massive wall of rock like that? Well, it's not one single event, not by a long shot. It's really a powerful combination of forces all working together. Some are invisibly small, while others are catastrophically large. And we're going to see exactly how they pull it off, step by step.
You see, the story of a cliff's collapse doesn't start with a big dramatic crash. No, it starts from the inside out, with a process called weathering. You could almost think of it like an inside job, weakening the rock's defenses long before the final fall. Now, the key thing to get about weathering is that it happens in situ. That's a fancy term that just means the rock is broken down right where it is. It hasn't moved yet. This is all the prep work, tenderizing the rock. And as you can see, it comes in three main flavors: mechanical, chemical, and biological.
First up is mechanical weathering, and this is just pure physical force. It's kind of like taking a sledgehammer to the rock, but on a much smaller and slower scale. There are no chemical reactions happening here, it's just brute force, breaking big pieces into smaller ones. One of the most powerful forms of this is called freeze-thaw, and it's amazing how something as simple as water can be so destructive. So water seeps into these tiny cracks in the rock. Then, when it gets cold, it freezes and expands by about 9%, and it acts like a tiny jackhammer, forcing that crack just a little bit wider. You repeat that cycle over and over, season after season, and you can literally split a boulder in two. And it's not just ice doing the heavy lifting. On the coast, you also get something called salt crystallization. Seawater gets into those same cracks, right? Then the water evaporates, and it leaves these little salt crystals behind. Over time, those crystals grow, and they exert this incredible amount of pressure that literally flakes pieces of rock right off the cliff face. So you've got two different methods, ice and salt, but they're both getting the same result, a weaker cliff. But the attack isn't just physical. Oh no, you've got chemical weathering, which can slowly dissolve the very minerals that hold the rock together, kind of like how acid rain eats away at a limestone statue. And then there's the biological attack. You've got plant roots wedging into crevices, animals burrowing through the soil. All of it creates instability for the final act. Okay, so once weathering has done its inside job and really weakens the cliff's structure, the stage is set for the main event. Now, gravity is just sitting there waiting to deliver the knockout blow. This final act is called mass movement, and it's pretty much exactly what it sounds like. A huge mass of rock, soil, and debris moving down slope, all thanks to the pull of gravity. This is that moment where all that weakened material finally gives way. But mass movement isn't just one thing. It comes in a few different flavors. For coastal cliffs, like the ones we're talking about, we mostly see three main types of collapse: blockfall, rotational slumping, and landslides. And as you can tell from these pictures, they each look and act very differently. This table here breaks it down perfectly. A blockfall is the most direct. A chunk of rock just detaches and falls straight down. A landslide is more of a chaotic, sudden flow of a huge amount of material. But rotational slumping, that one's unique. Here, a whole section of the cliff slides downwards along a curved plane, almost like it's slumping down in a giant chair. And that specific movement creates a very distinct shape. Now here's a really cool part. These collapses, they aren't just destructive events. They're actually creative. Every single time a cliff falls, it's actively reshaping the coastline, sculpting entirely new landscapes at its base. Let's take a closer look at that rotational slump again. The key ingredient, as you can see, is water. A ton of it. After a lot of rain, the soil and rock gets saturated, making it super heavy and weak. And eventually, it just gives way, sliding down that classic curved path. And the visual result of that is just unmistakable. You can see here how a sheer, straight cliff is totally transformed into these curved, step-like terraces. It's the distinct footprint left behind by a rotational slump. Okay, so what about all the rubble from those more chaotic block falls and landslides? It doesn't just disappear into the sea. It piles up, right at the base of the cliff, creating this massive collection of fallen rock. And this big pile of debris, it actually creates a brand new landform called a talus, or a scree slope. You can see how it almost acts like a natural shield.
It's this ramp of fallen rock that protects the base of the cliff from the crashing waves. And this is the really crucial point. The destruction of the cliff face leads directly to the creation of a new protective feature.
So this is all fascinating geology for sure, but it's not just some abstract science. These processes have a direct and pretty powerful impact on our lives, especially for anyone who lives near the coast. To put it simply, cliff collapse is a major hazard. Homes, roads, entire communities that are built near the edge are at constant risk from these very natural and ongoing processes. So understanding them is really the first step to living with them safely.
So, what can we actually do about it? I mean, we can't stop gravity, right? But we can try to manage the risk, and this often involves engineering solutions. Things like cliff drainage, which helps remove that excess water to prevent saturation, or slope regrading, where the cliff is reshaped to make it less steep and a lot more stable.
And here it is, the final crucial twist in the story. As destructive as this whole process is, it's also essential. All that rock, sand, and soil that erodes from the cliffs doesn't just vanish, it gets carried by the waves and deposited along the coast, building the very beaches and dunes that act as our best natural defense against big storms. So in the end, we're left with this really complex relationship. We need to protect ourselves from cliff collapse, but we also rely on that exact same process to protect our wider coastline. It forces us to ask a pretty fundamental question. Our coastlines are not static lines on a map. They are alive and they are constantly moving. Are we truly prepared to live with that?